Well, thank you guys for joining my session. I hope you enjoy it as much as I enjoy working with these new tools. So I have a few questions. If you answer honestly, have you heard of prompt engineering? Raise a... Oh yeah, of course, of course, of course. All right, and this one. Are you a great prompt engineer? Who here is very confident in their prompt engineering skills? Really? Okay, okay. People are a bit more shy with that, I guess. All right, well, this is my thoughts on prompt engineering. Believing in prompt engineering is like believing in magic. You know, trust me, I'm a prompt wizard, because you can say, do not hallucinate, and the spell obviously is gonna work, and basically what I'm trying to talk about is kind of like prompt engineering, but more scientific, because prompt engineering to me is like trial and error, just like throwing things and seeing if it'll stick. And it's not very test-oriented. And what I'm, going to talk about is, so why should prompts evolve? So let's talk a little bit about that. Well, let's talk about my evolution. This is not my first time in Build Stuff. I was here 3 years ago in November 2022. And I was very excited. Great crowd, great stage, great everything, I had a blast. I was speaking at that time, I was speaking about tracking my dog for potty training with a Raspberry Pi. It was a fun little project. Very quaint for nowadays, doesn't seem nearly as fun, but yeah, it was interesting. And now I was tracking my baby last year, also with computer vision. I enjoy that. 91%, you shouldn't be awake, but All right, well, that was last year. All right, so, well, this year I'm, tweaking other things, running other projects. A lot has happened in the last 3 years. Most notably, something, and I think it's been discussed already on the stage, something prominent happened 3 years ago in a few days by now, November 30th, 2022. Who can guess what it was? You spoiled the fun. Yeah, it was ChatGPT, right? And this is the evolutionary tree of LMs, right? Well, of course, it didn't start with ChatGPT, but pretty much this all is what it's branched out, right? And there's a lot more. Really, this is like a simplification. If you actually put all the models that are there, it'd just be like the other part would be like tiny, It's exponential. So what is a large language model? A large language model, well, at least the ones that most people are familiar with, I'm not talking about the other ones on the other side of the tree, BERT and whatnot. I'm talking about decoder transformers. Those are autoregressive. So what that means is they're just predicting the next token, in other words, the next word. They're nothing more than that. So a lot of people think, oh, well, how can it be? It's only that? Well, yeah. They're glorified next word predictors. And yeah, they're probabilistic. So they can take all these different routes. Some are more likely than others as you're predicting the next word after another, after another, after another, right? And as I said, they're nothing more than that. They're just the model. They have no memory. They have, no tools. They have nothing, right? So what adds that capability? AI agents. So AI agents is just a series of steps, a series of processes that interact with the LLM, that carry that logic forward, that integrate tools, that integrate memory, and whereas using just the LLM on its own, it's just input and output, like any other model, right? So AI agents are deterministic. And some magic happens with that. Oops. So the deterministic step is, can be unit tested, and, it'll be fine. You can incorporate another deterministic step, and you unit test it, and it's fine, right? It's where the LLM comes along, and it's the LLM dependent step, and that's where the failure most likely happen. So it's a big problem. However, it's the source of fragility for sure when it comes to agentic systems, but it's also a source of strength. Because if you don't have that probabilistic engine, you can't do anything creative with it. And that's important, because if it was just a bunch of if, for loops and if statements, like there's nothing interesting there, nothing unexpected. And it can really act according to unexpected inputs, which is what the LLM can do. So I'm also a strength, right? So I'm going to teach you about a classic prompt sandwich. I don't know if you're familiar with a prompt sandwich, but in agentic systems, we use a lot of them. And there's many ways of configuring a prompt sandwich. You got the buns, you got the lettuce, the tomato. There's more than one thing that goes in the middle. Sometimes you even put it underneath the sandwich. So it's a weird sandwich, right? But you start with the system prompt, most usually. That's where it starts. And you usually start with some tonal thing. It doesn't necessarily have to go like that, but it's like setting the stage. This is what you're supposed to do. This is not what you're supposed to do. This is how you're supposed to interact with the user. And this is assuming it's a conversational agent, because that's not the only kind of agent. There's other kinds. If it's a reporting system, summarization engine, or something like that, it might have a different kind of instruction. But it usually starts with something tonal, right? Then there's the retrieve data, which sometimes is in there, sometimes isn't. Sometimes there's history, which is also data. Might have something, some tool instructions, like here's an example. I don't know if you've been reading along, because I haven't, but yeah, it's assuming it's like a travel, kind of agent for Lithuania. So it retrieves some data, and that data is about, what it costs to do a tour, right? A day tour. And so if the question is, what does it cost to go, and it retrieved this data, it's probably going to answer the question correctly. So there's some kind of magic going here, and there's systems that find this retrieved data so they can answer the question. It's just not going to put everything in the context in what it's called the prompt sandwich, right? Because that's like the equivalent of, like your, not only your RAM, but your, like, the memory you have, like, closest. Probably my brother could probably explain it better, but it's just really the memory you have at hand at the moment, right? It's not just a collection of memories that right? But, and you have to retrieve, but it's just like most recent kind of memory. The problem with these systems is that you have a lot of different prompt sandwich, and it becomes messy, right? And it's pretty much like a machine held together with chewing gum and duct tape, because the prompts, they're iffy. They're not exactly like, they're not magic, right? Nobody's a prompt wizard. We have to become prompt scientists, it's not good enough to be a prompt alchemist. We have to elevate, right? So how do we do that? How do we stop making this Rube Goldberg machine where, sometimes the ball will hit and sometimes it won't, and sometimes things will fall apart like dominoes. We don't know what will happen. That's no way to do business. If your business depends on this machine, you're screwed. Pardon my language, but yeah, definitely not. So There's this new science behind it. You could call it prompt science or something like that, but they're calling it context engineering, right? So yeah, pretty much is that. It's no longer okay. I'm just focusing on one prompt. I'm focusing on making sure that the right prompt is at the right time and it's tested to be the right prompt. So we have to make sure we test that. And it's not just the prompt itself, because sometimes when I talk about prompt, I'm talking about the system prompt, but it's the prompt sandwich. So one way of doing that, and I'm going to discuss that at further length and show a demo, is genetic algorithms. Because genetic algorithms can battle test these things, can take pieces of prompts and kind of merge them together and see what is exactly the best way of interacting with the LLM, giving it instructions so it makes the most out of the data we're giving it. That's mostly the use case. There's other use cases for it. For maybe you're not providing data for it. Maybe you're trying to just figure out if someone is going to do a prompt injection or something like that. In which case, and they might do it before you ever retrieved any data, but that's a different kind of use case. So, but we're going to discuss a little bit of that in detail too. So, genetic algorithms, they start with initial population. So imagine just a collection of ones and zeros that you put in randomly. These ones and zeros are assigned to something that you have, a variable, right? So that's a variable that you turn on and off, like a gene, right? It's a gene that's expressed, or it's one that isn't, right? So it's a feature that you have, a feature that you may not have, and so you're testing if a collection of ones that are on or off are going to work, right? So then you somehow test fitness. In other words, you have a metric to which you test how well each one of those samples from that population work, right? So you have to have some kind of fitness way of determining fitness, right? So if you equate this to biology, you would say, okay, well, this is a person that has the condition to mate, right? Because that's pretty much what it boils down to, It's either, mate material or not, right? So there's a selection of parents based on the ones that are most fit, right? And these ones mate, and you end up kind of combining the ones and zeros from each other, right? And this is, of course, not all. Not all genetic algorithms exactly have this formula. This is probably the most vanilla version of this, and they're not always ones and zeros, just so you know. But it definitely kind of follows some kind of these kind of steps, right? And then mutation, you randomly mutate a few of the genes, just so there's variety. And sometimes you'll even copy the same, the same children that you created, and you just randomly, mutate a few of them. You make a few mutants, if you will. And then you just continue going. You assess fitness, you select, you mate, mutate, and the way it ends is after you've said, okay, this is the certain amount of generations that have happened with this population, and that's where I'm stopping, or you reached an optimal metric that you were looking for, or you said you had it already plateaued. So it's not improving after several generations. So you're like, okay, it's not improving. Well, I'll just leave it there. So how do you apply genetic algorithms to a system prompt, right? There's several ways of going about it. I've tried quite a few of them. So first of all, you would have to ask, what's the gene in this circumstance? So you could say, well, a gene is a word. So I'm either turning the word on and off. I mean, that's a way. Or maybe I'm replacing the word with something else. Um, or maybe I'm just going to choose something bigger. Let's say it's a gene, but it's really a collection of genes. So it's a sentence, right? I'm replacing a sentence. Or maybe a paragraph, you know? Or maybe I'm just dealing with the whole thing and I'm replacing everything every single time. So what we replace it with is gonna vary, you know? We either omit it altogether because we figure, well, maybe never insult the user is like redundant, you know? Why would we tell the LM to do that, you know? Or maybe we want to permute it. We want to take that and change the wording and see if that makes any difference. But that only matters if it's relevant to what we're trying to test. Like if we're trying to test toxicity, right? That makes sense. Otherwise, it might not. It might not change the metric altogether. So we can be very specific in what sentence we're targeting. We say, okay, we don't care about anything else. We're just testing that one, right? So there's different ways of doing that. So the one I'm going to talk about now is genetic Pareto, and that's a newer algorithm, and that's the one I'm going to demonstrate. And it starts with you give a GPA a program, and the program is just where like the configuration is stored, and it just has all the like the basic configurations, and you know certain functions that are required. And then you have the metric, which is how you measure fitness. Then you have a training set, which is what you use to kind of create the mutants, if you will, as examples. And the validations test, which is how you test if they're, you know, if they're fit, if the prompt is that you created or prompt candidates are fit. And then you have a budget. And what the budget means is how many generations you want to spend on this experiment, you know, or to what metric you want to achieve. You know, where is it you want to stop? So first you create a baseline evaluation, then you have reflective diagnosis. In other words, you know, what went wrong. Then you do mutation. This skips some of the steps that you saw previously. So this is like an interesting like variation. So you just go directly to mutation, because the thing with this one is that it's like I had explained. I probably it's not a better way of explaining it, but it's completely mutating the entire, not a specific gene, but the entire genome, like if you will, the entire prompt is being mutated, right? So that's how it creates new candidates, and it uses it based on representations on how it went in previous iterations. So it'll say, okay, well, these were the most fit ones in previous iterations. These were the least fit, and then somehow it's gonna figure, well, maybe these were the commonalities. These were the reasons. So that's how it creates the mutants. And then evaluates the candidates that resulted from mutation. It does a selection. It mates, and then it iterates till the budget has reached, the improvement plateaus, or the target score is reached. So, and that part is fairly standard. So now, without further ado, I'm going to demonstrate how we can do stuff with GPA. But first, I have a question. Well, actually, several. But yeah, let's go through the cases, and I'll let you guys vote which one you prefer, you know. There's time I might do several, but you know, I don't promise. Okay, the first one is, you know, imagine the sales guy. You know, he's kind of lazy. He's like, okay, well, I have this bunch of, you know, data I'm scraping from online of people and where they work and their information. I'm just going to try to use LLMs to extract the information. So I want to figure what's the best prompt to extract that information correctly, right? So it's like a document extraction problem, right, or data extraction problem. So we're going to try some of that, and then option B, text to SQL. So imagine you have a question like how many orders are from customers in Canada, and so it's supposed to come up with this SQL, right? And I made it tricky on purpose. Obviously, you don't expect orders. There's notation that's differently. Some people use, but that's just so it wasn't that easy, because sometimes it's not so evident. Because that way it has to figure that it'll have to create the right prompt so it matches the right syntax. And this one is intent classification. So imagine, you have customer service person, and they want to implement, maybe through the phone system or through the email or through chat. Someone asks a question, and so how do we route that question? That's a fairly common use case. More and more, there's more discussion how important it is to route, queries appropriately and have them dealt with by specialized agents, specialized models, or even specialized humans. So that's very important. So this one is for, let's say there's a label that's called change shipping, and that's how it's supposed to classify that one. And then this one is red teaming a guardrail. So imagine Marvel created like a chatbot, and they don't like it when people try to pit them against DC. They're like, come on, don't do that, right? So they have to put some kind of guardrail in their prompt to make sure that people aren't like doing that. So that's it's supposed to answer something like that, right? If someone gives them that, it won't like engage in that kind of conversation. So those are like the 4 options. Option D, option C, which is like the customer service. And this is like, data analyst. Forgot to mention the data analyst. There's a lot of use cases. There's more and more data analysts and business analysts that don't know how to program. And sometimes they're just faced with a data lake, and they're like, what should I do? I don't have it. And if the company is kind of cheap and doesn't want to invest in some kind of tool, they just have no choice but to learn SQL, right? So it's a common use case. So what should it be? Choose your adventure. A, D. D? Okay. Yeah, I'll just hide this over here. Let's go over. I just want to show you guys the interface first. You see, I think it's already set up that way. Oh, can I close that? Yeah, no, I think I put it. Oh, there it is. So I'm going to show you a toy example first, so you get familiar with what goes on. And you can see here, this is where things will show up in this one. Here I have open like the front end. It's a Node.js, and here's the backend. It's a Flask, Python thing, service. And so, can you see this well? Yeah, I'm guessing you can. But I can zoom in. Don't worry. Right. So these are all the configurations. Here I can select what kind of optimizer. It's by default the one I discussed, GPA. And then here is the configuration. Unfortunately, this part is kind of manual. I didn't like drop down it yet, but I'll show you how it works. And so here's all the different configurations that you require for DSPI, which is the library that does this. And so here I can show you, here I just click on run. I don't have to go over all the different settings at the moment, but basically I can zoom all the way out so you can see because it's kind of interesting. But there, it's kind of tough, right? And see, you start to see some things going on. It's doing all the different things. So it's coming up. Each one of these is a generation. And sometimes the generation will have more than one. And the thing is, the generations, in theory, are not supposed to be more than one, but it's never going to show 0 scores. We've got 0 scores, which is not going to, they're not even going to mate. So it's not going to show up. So see, here's a winner over here, and here's another winner over here. So you can zoom in here and see the different prompts. Of course, this is just for like visualization. There's definitely better ways of seeing this. Like if you wanted to just show the best prompt, it shows up here and it outputs it. So it's not, it outputs it in the logs and everything. I'm trying to zoom in. I don't know why it's not letting me. Oh, here it is. So see, all this is the prompt it came up with, the best one. And here's all the siblings, all the different variations that came about. So there usually is a point in which it happens to coalesce into a series of good candidates. But sometimes it has like a slower start. Another thing that you find that's very interesting about this process is that the first prompt is usually very short. It keeps like expanding as it learns to add more things. Occasionally, it takes a step back and it realizes a few of those, it took some missteps, and so it goes backwards and it becomes shorter, but just for one generation. But yeah, that's usually the case. See? Yeah, and something I don't know if you noticed, hopefully it's visible, but you can see the score, right? So this is a toy example. I'm going to get to the red teaming thing right now, but it's a toy example. So I'm going to go over right now to the code. So oops, that's not the right screen. Yeah, the code is underneath. Okay. All right. So I'm not going to go too deep into the code. As I said, there's 2 parts to it. There's the back-end code and there's the front-end code. I'm going to show you, for now, the data that has to do with this red teaming exercise. This is the Marvel guard. And this was synthetically created. It's not like, it's also, in a way, a toy data set. But it was meant to be hard on purpose. With an exercise like this, you really don't want it to be able to achieve it. I mean, in an easy way. You want it to be hard because it is kind of hard to tell the LM, don't do this, and people will find a way sooner or later. And if you use very simple examples, it's not gonna be able to prove that it can. So it's like if a bank wants to prove that it's safe, it has to hire the best hackers, the best. Yeah, so it's kind of like that. All right, so yeah, you see that here this is a CSV file, and what you end up having is, on one hand, you have the question that's made along with some guardrail prompts, and then after that you're going to have the answer is supposed to have, and so it's going to find that the answer that comes back is closely resembles the one that it ended up having. So that's within data sets. And if you see here, this is the configuration for model guard. So when I mention, okay, metrics, the metrics are defined in this file over here. and the configuration points to this. And this is how it calculates the metric. Yeah, it does like a similarity kind of heuristic for that, I think. And the program is very simple. The program is just it follows the template that comes with DSPy. Speaking of which, how many of you are familiar with Python? I didn't ask that. Really. Okay, good. My kind of people. Yeah, I think it's all it's basically the most important thing here is the metrics, and the thing that loads the data, right? Um, and then once it does that, then basically you just have to tie it into the front end. And so as I mentioned before, that's unfortunately something I still do manually because I hadn't put it in the dropdown. By manually, I mean going here and saying, okay, well, I'm going to copy this and replace it with toy. Oops. So replace, and we're done. All right, so now I refresh the screen and we start over. And well, I can verify that it has the right one. And as you see, it has all the configuration details from the Marvel example. So it's going to point to the right program. It's going to point to the metrics. It's going to point to the right training set, to the right validation set, and all that. So that's what I mean by configuration. And I just hit run. And we should see something happen here, hopefully. Oh yeah, it is going. It's going. I just wasn't in the right place in the terminal. So as you see, it's trying different. I can make this bigger, so you can see. Oops. Yeah. So you can see it's trying all these different prompts, and a lot of them are scoring 0, which is great. Eventually, you want some of them to be learn to get a few of them. You know, I've run this a few times, and it's only managed to get a good prompt like, you know, once or twice. But it is an interesting experiment to see if there's some way, because it's completely adversarial, and the idea is for it to figure out a way to beat the kind of questions it's going to get from users. So let's imagine somewhere there's a horde of DC comic fans that are trying to mess with Marvel IT, the IT folks in Marvel. So another thing to note is that every time it says average metric, and every time it does a test, it's not doing a test on obviously a single sample. It's doing a test on various. And so another thing to note, it's fairly quick, and the reason it is, and something you could definitely test an even better LLM. It'd be more costly. You know, obviously, since I've run them this thousands of times, I use ChatGPT 4 Mini. You know, you could also use a local LM, which is also fun. And one of the cool things about DSPy and a lot of these libraries is they're based in Light LLM or one of these other libraries that you know, can universally support, you know pretty much any cloud service LLM, any local LLM through Oyama or one of those. And so it is really cool. Yeah, I'm not seeing anything yet. Yeah, I think this one. Yeah, it's still trying. It's trying to beat it. Oh, the grading function? The grading function, what it's doing is trying to figure out if the keywords, because let me see over here in the code. Yeah, it's a heuristic. It's a heuristic. In the case of all the ones that I showed, there's one that uses an LM. You can, and that's something we can get into. If you go to the metrics, and something I wanted to show, and I forgot to because I mentioned it in the description in the abstract. There's a lot of cool things you could do with something like this. Like for instance, you could input an image, and you could then have no, you could output an image. You could have a prompt that outputs an image. Then you have another LLM that interprets that image, multimodal one, or you could have image to text, one that captions the image to tell you what it sees. And then you look for keywords. Like for instance, you could say, okay, I want a blue car, you know, in front of the red sunset, or something very specific. You want to make sure that it did follow the instruction of blue car. So you're gonna first create the caption from the image it generated. Then you might use an LLM to figure out that does it say there's a blue car? Did it follow this instruction? Or maybe you could use a heuristic where you just figure out if blue and car are in the caption. So there's many ways of going about that. And you can put that in the metric where you're testing these things. You're testing how many times where you ask it to do this instruction it followed through, right? And there's a lot of different things you could do in metrics, and one of them, in only one of the examples I do that, is use an LLM to interpret the output, right? Because it's more expensive to have to do that, but sometimes that's the only way, right? To make sure that it did it correctly, because creating a heuristic behind it is too complicated. Like for the document extraction ones, it's fairly simple because you're like, okay, did it extract precisely these entities, these words from this text? Either it did or it didn't. For classification, it's the same thing. But for other cases, it's more nuanced. For a summarization problem, did it summarize this text correctly? So there's a way to do it, which is probably like the LM as a judge is a good option, but there's other ways of making sure that's a bit more grounded, especially if you have already like data, you already have a human summarization of a text. So let's go here back to you wanted to see metrics. Right, so metrics for the Marvel Guard. Yeah, so I have two heuristics here, right? And only if it meets both heuristics, then it passes, right? So if it and yeah, I thought it was something more sophisticated, but I'm just looking if it has the patterns of refusal. And these are the different patterns of refusal, or the regular expressions. So if it meets any one of these, then it meets that. And then if it uses any of these tokens at the same time. So it's not very sophisticated as a metric, to be honest. I mean, as I said, this is just an example. I could have done something more sophisticated. And that could be one of the reasons. I haven't looked at the logs every single time, to be honest. So maybe there are times that I'm unfairly grading it. Oh yeah, it got a winner this time. All right, that's cool. A score 0. Not a good winner. All right. We can test another one if you're curious. There's other ones that are not as hard as this one. Like for instance, a classification problem for customer service, or it could be the sales problem. Well, or which other one? Or the SQL. The SQL is an interesting one too. Takers? Customer? Okay, cool. Yeah, graph view. Keep forgetting it's here. Oops. Intent. Oh, it got it right away. That's easy. All right. Yeah, sometimes, occasionally, it's just like in the initial one or two populations, it finds an answer. So that's interesting. You know, I sometimes you run it and it takes like 2 or 3 generations, and sometimes it takes one. Sometimes it takes 7 or 8, you know, to reach its mark. But turns out the instructions are that simple, you know. Okay, I guess that's not very fulfilling. It's all about having the right data set. And something to say, since I synthetically created these data sets, it's fairly easy to make a synthetic data set that either skews too much on the easy side or too much on the hard side. There's a science behind making it like the right balance. But if it was a real data set that I had downloaded, I thought of doing that. You know, for some of these problems, like the customer one, there are some real data sets for classification. You know, probably should have done that. But let's try SQL. I think that's a no. Okay. And you can see, yeah, I haven't done during this presentation this debugging where you look at the prompts and see what the differences are. Yeah, if you're really engaged with the problem, if you're really like, this is a real, in this case, this is a demo, and you could really spend a lot of time looking at these prompts and seeing what happened. And it's fairly interesting. I've used it for work stuff, so I know this from experience. I wouldn't share the work examples because I can't, but yeah, it's interesting. So I don't know if you got. Oh yeah, I have a few more slides. If you, well, not really. I think it's just like final thoughts if you want, and I'm open to any questions. So like basically, like this is one of the initial steps in like context engineering. I would say you have to test things. Maybe not only the first step, but also the last step. It's also very iterative because you take a prompt and you refine it. In this case, one of the good things about GPA is that it can start from zero. You know, you start from no prompt, right? In other kinds of scenarios, you're starting with a prompt you already have because you need something to take something away or to permute it in some way. But with GPA, it's not like that. So, but usually you're trying to refine a prompt, you're trying to make it better, and then you realize, well, This time I need to use it in this other way, or I need to use a different tool, or I'm reorganizing my agent so it's doing something else. So that means kind of refining things. So context engineering, there's like really common challenges in context engineering. There's domain knowledge that's required. Like I work in agriculture, I can expect the LLM to understand some of the terminology. Strangely enough, it's not like the corpus that trains these LLMs is well versed on, like, some weird bacteria that is in the soil or something like that, or maybe a synonym for something, or different codes that we use for different agricultural terms. So there's domain knowledge that's required. There's temporal and geographic elements, like it doesn't know what day of the year it is, what year it is or what day it is. It doesn't know, where we're located, where the user is located, right? It might be missing some steps. It doesn't know, okay, these are the steps I want you to take, right? And then there's prompt-based solutions to a lot of those things. You can provide the basic domain knowledge. You could provide the current date and location. You could provide detailed instructions. You provide detailed data dictionaries for source data. That's often a problem. Like you put in data in the context, and you have abbreviations, synonyms, weird artifacts, and you're not really explaining this is what this means. So it's not going to understand your schema unless you provide it. And then another thing is there might be confusing data structures and naming. There might be irrelevant and contradictory data sources. So these are solutions you can solve on the data side. So you bring the data to the LM, you make it as self-explanatory as possible. And it doesn't hurt to also provide some explanation. And that's something you can also test, because you don't necessarily want to put something in the context if it's not needed, right? So you could test that. And then other challenges, you got poor fitting architecture, orchestration flow challenges, infra speed. Of course, there's cost. I didn't mention that. Like you might want to use the state-of-the-art LLM, but it's costing a fortune token-wise, so you just have to cut back on that. And then there's tool API specific failures. There's parsing and transformation issues. And then there's data quality. And then there's data privacy and security. Of course, if you're bringing things into context, and this is in the cloud, and then there might be some leakage of like personal identifiable information to a cloud-based LLM. So there's a lot of different learnings there. We could go into detail into any of those if you guys have questions about them. But I mean, this concludes this session, and appreciate it.